which is about chemical equilibrium. So we talked about in general what really chemical equilibrium means. So as we talked about before, chemical equilibrium again doesn't mean that when we reach equilibrium that we have the same amount of reactants and products and those type of things. What we are talking about when we reach chemical equilibrium is we're actually talking about the rate of the forward reaction versus the rate of the reverse reaction. So when we do reach that chemical equilibrium, it is when we have that forward direction and that reverse direction, basically the rate of each of those basically equaling each other. So what that essentially means is whatever sort of concentrations, if you're sort of dealing with pressures at that point that everybody is sort of locked into at that point, they basically will be able to maintain it because just as quick as sort of do reactants come together to make products, just as quick those products are kind of reassembling and going back the other way. So sort of a back and forth that gets everybody basically locked into place in terms of where they are in terms of their concentrations. Now, we talked about a relationship that you can have in a sort of reversible reaction like that, which is the equilibrium constant, and that is K. And that's capital K, which is basically our products divided by our reactants. And we also do use the coefficients in the balance equations as the exponents when we do that. So when we take the concentration of our products over the concentration of our reactants, we use the coefficients as those exponents for each of those. And the nice thing about that is it is an equilibrium constant. So as we talked about last time, you will get a sort of constant value for that number. And it is just a number, no units associated with it. But you'll get a constant value regardless of sort of what you start with in terms of that reaction. So, if you start with different amounts of the reactants in a particular experiment, and then you kind of change it up and change those starting amounts, maybe throw some products in there. As long as the temperature remains constant or stays the same, the ratio of those products to reactants will essentially always come out to the same number. Again, it really only changes when we change the actual temperature that we do see a difference in that value, and the differences between really the value in the two temperatures. So again, as we talked about last time, if we change the temperature, say to 50 degrees, it will again remain constant, that value of K at 50 degrees, unless you again change the temperature. K does tell us some information about what's going on in the reaction, as we talked about as well. If we have a really large value of K, that essentially means that when we reach equilibrium, we would mainly expect to have products being present, and vice versa. If we have sort of a small value of K, what that means is when we reach equilibrium, we would mainly expect to have reactants present. The big number there in terms of a large value is basically anything above one is considered large, anything below one is considered relatively small. We also talked about that you can write a K value, which is sometimes referred to as Kc, using the concentrations. You could also write a Kp value if you have more pressures sort of given to you. They don't really equal the same number, but they do give you that, again, that same sort of information as to whether or not you have mainly reactants or products at equilibrium when you sort of reach equilibrium. But we did see an equation that allows us, or a formula that allows us to go between those two, and that was this one here that we talked about last time as well. And that's the Kp equals the Kc times RT delta N, R being our gas constant, that 0.08206 number, temperature in our Kelvin. And as we talked about, important when we do our delta N, we want to make sure that we do take the products minus the reactants, and we do not want to ignore anything that may end up being negative, because again, mathematically, there is a difference if you got a 1 or a -1 in terms of when you do the delta N. So you want to make sure you watch out for that. We then, towards the end of the first lecture there, talked about how to manipulate reactions and sort of the K values, what happens with them. So the main things that we sort of talked about is if you sort of add two reactions together, you multiply the K values. If you reverse a reaction, you take 1 over the K value. If you need to sort of multiply by a common number, you take the K value to that common number. And if you need to divide a reaction by a common number, you then would take the root of the K value to that common number. So again, those are multiple ways that you could sort of manipulate sort of reactions. And this would be a case like we talked about last time that you might want to use a bunch of individual reactions to sort of build an overall reaction and try to figure out what the K value is. And then lastly, we got into actually solving for equilibrium concentrations using ice tables. We use the ice table to help us. Ice means initial, change, and equilibrium. Initial, we go usually with molarity, our atmospheres for pressure at this particular point. We use X to represent the change, and we want to make sure in that change part that we do use the balanced equation, those coefficients for stoichiometry purposes. So for example, coefficients A2, we would do something like minus 2x. Coefficient was a 3, minus 3x, and so forth. We basically will solve for x, and that will require perhaps some quadratic formula like the example we did last time, may be a little bit more simpler than that. And we'll see a few more examples here today. And that will allow us to figure out the equilibrium concentrations. And before that, we talked about also Q, which is the reaction quotient. And that is basically calculated the same way as K. And it helps us determine whether or not we have a system that's at equilibrium. And if it's not at equilibrium, which way it needs to go to reach equilibrium. That was a lot of stuff there that we talked about last time. Any questions on any of that stuff before we kind of continue on? Okay, so again, a reminder, if you do have questions, you're welcome to unmute yourself and ask, or again, you can throw it in the chat box there. So we did that first example, I think, involving an ice table. So why don't we pick up with this one here? So why don't you take a few minutes or so, maybe, and work on this. May take 5 minutes or so and kind of see what you come up with. And then we will talk about it. So again, try to follow those steps of the ice table like we did. The goal here is, again, to figure out what X is. That will allow you to figure out what the equilibrium values are for each of these. So why don't you work on it for a few minutes here, and then we'll kind of pick it up, see how everybody's doing. And here of 0.5 moles of H2, 0.5 moles of I2. Place in a 1 liter flask at 430 degrees Celsius. We're looking for what everybody's concentrations are once we reach equilibrium, and they do give us a K value. So this is definitely an ice table type problem. We have our initial, we really have our initial moles, and we do have the volume, so we can calculate the molarity from that. And in this case, since it is 1 liter for everybody, it makes it relatively easy to calculate the concentration of H2. It obviously would be 0.5 moles per 1 liter, which obviously equals 0.5 molar. Same thing will be done for I2. It will also be 0.5 moles per 1 liter, also giving us 0.5 molar. So again, we do have the starting amounts of both of those, and we want to figure out what our equilibrium concentrations will be. So we will set up our ice table. And if we do that here, just rewriting the equation, H2 plus I2, 2HI. Initially, we would have 0.5 molar for our H2, 0.5 molar for our I2. And as we talked about last time, if they pretty much just give you kind of the starting amounts to reactants and nothing is said about the products, you could probably safely assume that you're starting with 0 there initially for your product side. Any questions on that so far? Now, the change part is where we're going to use X, but also important, as we talked last time, we want to make sure that we do take these coefficients into account, because that's going to give us the right multimole relationship. So if you don't do that, really, you'll have the wrong stoichiometry when you go to sort of calculate this. The other sort of pretty safe assumption that we can make in this case is, since we are given just the reactants and nothing here on the product side, it's probably pretty safe to assume that this reaction is heading towards the product side. And what that means is we would expect our reactants to decrease with time, and we would expect our products to increase with time, and we represent that with minuses and pluses. So on the left-hand side on a reactance, this should be minus x, this should be minus x, and this would be plus 2x as we expect it to increase, and also because of the coefficient there. Any questions on that so far? So as we talked about last time, we're essentially just going to bring this down. So 0.5 minus x, 0.5 minus x, and 2x. Any questions on sort of how the ice table looks, how we got any of those sort of numbers or anything like that?
What did you say that we are assuming going from left to right?
Oh, so it's a pretty safe assumption in this case that the reaction is probably going to proceed from left to right, because we weren't given any information about products or starting with any products. So really in this case, if you remember maybe those earlier graphs that we saw, maybe the second or third slide, that, when the reaction starts at say time 0, if while we have a reactance, there's really no products, so 0. So in order to make products, those reactants has to start coming together. So since we weren't getting any information that we're starting with any products, we could probably assume that this reaction is right at the very beginning of it, which means we probably have no products. So we have to kind of go to the right to begin with in order to make the products before we get enough products to head back the other way.
Okay, thank you.
You're welcome. Other questions?
How did you find the 0.500 again?
So what they gave us was that we started with 0.5 moles of the H2, and it was in a 1 liter flask. So we could calculate the molarity, right? Molarity is our moles per liter, right? So that's where we got it from, 0.5. And because it's all sitting in basically 1 liter for the volume, that gets us our 0.5 molar. Other questions on that? Okay, so at this point, as we talked about last time, basically the goal here is really to solve for x. And to do that, we're going to use our equilibrium expression to help us do that. So if we wrote the K expression here, it would be the concentration of HI, and we would need to square it again because of the 2, divided by H2 and times I2. And in this case, they did give us the K value, which was 54.3, I believe. So like we talked about last time in that example, we're basically just going to take our equilibrium line and basically put it into our expression and mathematically solve for x. And that x is going to represent the change. And we'll know, basically how much reactants basically that was lost. And we can figure out how much products was made in this particular case. So if we do that, up on top, we will have 2x squared divided by 0.5 minus x times 0.5 minus x. And that is going to equal 54.3 at this particular case. All right, so we do want to solve it mathematically. And one important thing to think about is you don't always have to use the quadratic formula to solve it. You can if you want in certain cases. But if you look at this, you might recognize that this is actually a perfect square on both sides. So you could actually just take a big old square root of both sides in this particular case. Makes the math a lot easier. And if you do that, it looks like we will end up there on top 2x, and on the bottom we will end up with 0.5 minus x. And the thing I always forget to do is actually take the square root of the 54. So let's take the square root of 54.3, and looks like maybe we'll go 7.36885. This is obviously going to make it a lot easier to solve for. We're going to then multiply the bottom to the other side. And if we do that, that will give us 2x is equal to, go 3.6844, just taking a couple digits, minus 7.3689x, basically. We're going to bring pretty much our x value to the other side by adding it back that way. And that's going to give us like 9 point, we'll round a little bit, 3689x is equal to, so I run out a little bit of room, 3.6844. So dividing that by 9.3689 gives us something like a x value of 0.393. Any questions on that math there? So when we do get the x value here, that is pretty much all the x's that we see in our equilibrium line. So that means that we can then go back into our equilibrium line and really solve for the concentrations of each of these guys at equilibrium. And if we do that, H2 at equilibrium would be 0.5 minus x, which was 0.393. And that would get us 0.5 minus 0.393, 107, 0.107. Again, we do need units there as it is a concentration. I2 would come out exactly the same. Again, from the equilibrium line, 0.5 minus 0.393, going to give us 0.107. And lastly, our equilibrium concentration of HI in this case would equal 2 times x, which means 2 times 0.393. And that would get us 0.786 molar. And these would represent the equilibrium concentrations of each of these guys when this system actually does reach equilibrium. We do see that, the reactants came down as we would expect. The products went up in terms of their concentrations. Any questions on any of those sort of steps there?
I'm still confused as to why the product side is increasing and the reactants is decreasing.
So even though it's a reversible reaction, in terms of where we're starting with is we're basically starting this reaction, we could assume basically at the very beginning. You could kind of assume it that way, which means at the very beginning, you could kind of think like you went to the shelf and you grab some H2 and I2. I'm not sure you could do that, but you went to the shelf, grab some H2 and I2, and you basically dumped it into this flask, right? And I'll draw my flask square, which is a new flask, also known as a beaker. So you dump this into this flask. And because really at the very beginning here, there's only H2 and I2 present, there is no products present. So in order to make products we know is going to happen, that means that this reaction does need to actually go to the right-hand side and start to make products. So that's how we know that the reaction will go to the right, because we were told in the problem really nothing about our products. So we could assume very safely that we don't have any products to start with. Otherwise, they would tell you, hey, in this flask, you have, 2 moles of the products or something like that. Other questions? Now, the other kind of, important thing, since this is a lot of math and stuff like that, that you can really kind of check yourself to make sure you didn't maybe mess up anywhere along the way in terms of calculations or anything like that. You can at this point, because these are the equilibrium concentrations, you could put them back into your equilibrium expression. And what you should end up with in terms of a K value is a K value that's very close to what the K value was in the problem, for example. So if we did that, I believe you do get something in the ballpark. And again, it's not going to be perfect because there's rounding and stuff like that, but you definitely should be in the same ballpark. And for example, you get about a 54 here, and that's pretty close to the 54.3 that was in the problem. So as I mentioned last time, it's a good idea if you do have the time, because, there's a lot of places where, some little mistake could kind of really mess up a lot of the math. Just kind of throw it back into that equilibrium expression, make sure you get a K value that's pretty close to what you started with. Otherwise, if you don't, then you should start looking probably through your math. Any questions on any of those sort of steps there?
Professor?
Yeah.
If you do it using the quadratic equation, you get 2 values that are under 1. Now, how would you figure out which one to choose?
So it should come out even if you did the quadratic, and I haven't went with quadratic all the way through with this one in a long time, but at some point you should get a value that wouldn't make sense. So either you may get a negative number or something like that, or alternative to that, if for some reason, neither one gave you like a negative concentration, you would probably want to put it back into your K expression like I just did here on the page. And one of them should be probably further off than the other from the true value of K. And that would be probably your last sort of way of doing that. But in most cases, when you use the quadratic formula, so we're talking about, there's a lot of different options in terms of the answers you could get. You could get two positive numbers. You could get a positive and negative number in terms of the X values from the quadratic. You could even actually get two negative numbers, but somewhere along the way, it won't, one of those numbers really shouldn't make sense in terms of either when you put it back into the equilibrium line, you get like a negative concentration, or maybe once you, if it could go into everybody, maybe you put it back into the expression, the K value is very far off from sort of the true value. So those would be ways you could kind of check in that case. But I would say probably 9 times out of 10, when you use a quadratic, one of the answers when you go back into the equilibrium line usually won't make sense.
Oh, so in this case, for the other value, I get 0.68. So if you plug it in at the start, you get negative concentration. I see.
Exactly. So that's usually the case that will happen. I very rarely have seen a case where maybe you get two answers, so you could put both of them in. But one of them really, when you put it back into that equilibrium line, will probably yield you a negative concentration. So as you mentioned, if one of the values got was 0.6 something, when you put it back in for H2 or I2, that's going to yield you a negative concentration, which you can't have.
Thank you.
Yeah, but that's a good point. Again, we will use quadratic a lot, and sometimes people get a little freaked out, like, isn't this always supposed to be sort of a positive value and a negative value when you get the X? And it can be, but you could also, like I mentioned, two positives, two negatives, and it will still work out. Other questions on that? Okay, so let's try another one here. We're going to use the, that's what we just got, hopefully. There you go. We're going to use the same equation, basically, but in this case, we have the H2, I2, and HI given to us. So 0.00623, 0.00414 for the I2, and 0.0224 for the HI. See what you come up with this one. I'll give you a good amount of time on this one. There's some good math going on in this one, so give it a go and see what you come up with. So let's talk about this first off. This one here, which is obviously an equilibrium problem that we need to do an ice table, and a couple little different things about this one, although it's the same one we were just working on. One difference is we are given, actually in this case, the starting amounts of actually everybody in this particular case. So in this case, we don't just have the reactants, we actually have reactants and products given to us. So when we do have the starting amounts of everybody, that's something that you should think about in terms of what we talked about last time, which is Q. And Q is, we want to figure out, is it at equilibrium? And if it's not at equilibrium, which way it needs to go. So this actually is another place where actually Q should be used as well, in addition to solving the problem. Not so much for the point of, is it going to be at equilibrium, which I would assume this is, in this problem, is not going to be at equilibrium, but it does help us decide which way it needs to go to reach equilibrium. So if we were to calculate Q, remember that you calculate Q the exact same way that you calculate K. So Q in this case would be HI squared divided by H2 and I2. And we would put our concentrations that they gave us, so 0.0224 squared up on top and 0.00623 on the bottom, 0.00414. And if we do all that, we get a Q value of 19.5. Remember that our K value here was 54.3, I believe, 54.3. So the K value is 54.3. That means in this case, Q is less than K. So as we talked about before, this is definitely not at equilibrium, which probably is not a tremendous surprise at this point. Otherwise, this wouldn't be much of a problem. But what it does tell us is in order for it to reach equilibrium, it actually needs to go towards the product side, right? So it needs to go to the right, our products. So you may be saying to yourself, why is that maybe important? Who really cares? And in this particular case, if you didn't do Q at all, you probably will be okay anyways. But really where it would affect, for example, if you look at a nice table such as this, is it would really affect the change part, right? So in this particular case, because this reaction is proceeding to the right, what we know is these guys should be minuses and this guy should be pluses as we go through it. Now, let's just say, for example, it was the opposite and Q ended up being greater than K, which it wasn't in this case. What that would tell us is, again, it's not at equilibrium, but to reach equilibrium, it actually needs to go to the reactant side, which would mean what it would affect in terms of the ice table is actually the change part. This would be minuses, and these guys would actually be pluses in that particular case. So, I would probably say that, 8 times out of 10, 9 times out of 10, even if you blew by this type of problem and you had everybody sort of given to you like it was here, and you just went straight into the ice table and solved it, you'd probably be okay. But there is a few occasions or some occasions where, it actually would be heading sort of in the opposite direction, which means if the product side, or sorry, the reverse reaction was predominant, we would expect in that case products to actually be decreasing and reactants to be increasing. So in this particular case, we just use Q, which just wasn't this guy, which wasn't this in this case. We use Q really to confirm here that, this is really the situation that's happening in this particular problem. Any questions on sort of that aspect of it?
Yeah, I have a question. So when for like how do I say this? Okay, so like we're going to the right for product, and you're doing that because the Q is less than or is greater than or sorry, is less than K, but we're trying to make it equal. Is that why we're going to the right to try and like
Yeah, so the idea here is, remember, so basically as we talked about last time, Q basically tells us two things. It tells us, is the system right at this point with whatever concentrations you have, is it at equilibrium already? So when we calculate Q here and it's less than K, it tells us first off, it's not at equilibrium, which we could kind of guess because it's sort of an equilibrium problem. So, we could probably make a pretty safe assumption that it's not. But more importantly, what it tells us is in order to reach equilibrium, basically go from our initial concentrations, which we now know these sort of are like our initial concentrations at this point, to get to our equilibrium concentrations, it needs that reaction to go from reactants to products in order to do that. So that's sort of what the Q kind of tells us here. If we happen to have calculated, for example, Q in this case, and it equaled dead on K, we would be at equilibrium, which means we wouldn't have to do any calculation at all. These actually would be our equilibrium concentrations in that case. But that obviously didn't happen in this case. And the other option would have been, like I earlier mentioned, that if we had the opposite occurring, it also would tell us that right now at this point, the system is not at equilibrium. But different than how we're going to approach this problem, in order for that to reach equilibrium in that other case, it actually has to go in the reverse direction to reach equilibrium. And that would obviously affect, which side is gaining stuff and which side is losing stuff in that particular case.
And so if it was at equilibrium, if we solve for Q, it would have been 54.3.
Exactly. Yeah. Are pretty darn close to 54.3. Are probably a textbook problem, it would hit exactly that number and stuff like that. But yeah, so if you did calculate Q and it did equal K, pretty much the problem would be over at that point, because what that would tell us is it's at equilibrium, and those then would be your equilibrium concentrations of those guys. Other questions on that?
This may be a silly question, but out of good habit, should we always be solving for Q before we go into the ice table? For example, like if it was an exam and we were given this problem, would we miss points for not solving for Q, even though you can kind of figure out that it's moving to the right without solving Q?
So it's actually a good question. So a couple answers to sort of your question. The first one is you won't be able to always calculate Q. And for example, the problem that we did previously, or even the two problems that we did previously to this one, you didn't have enough information to solve for Q. So really the only reason we're able to actually solve for Q in this case is because we were given information about not just the reactants like we did in the first couple, but also the reactants and the products. So that allowed you the ability to actually calculate Q and actually verify sort of what's going on. And to secondly answer your question, yeah, you probably should calculate Q if it is a situation like this on an exam. But again, there will be a lot of problems like the two we did previously, maybe the next one as well, where you really can't calculate Q because you just don't have enough information. And in those cases, it's pretty safe to assume that, you know, it's going to probably go to the product side if you're not given anything in terms of products given to you in the problem. What I was saying earlier about a problem like this is sometimes people do sort of blow by sort of the Q aspect of a problem like this. And, you know, probably 8 times out of 10, even probably more than that, you'll probably still be pretty safe in almost all cases to assume that's going to the products, but it isn't 100% always sure that it's going to be heading towards the product side and all kinds of problems. Other questions on that?
Thank you.
You're welcome. Okay, so let's actually now get into the, I don't know if I'll classify it as fun, but let's get into the actual solving of the problem. So now that we pretty much assert ourselves that this reaction is going towards the product side, we can actually get into the actual ICE table here and try to figure out what's going on. So initially in this case, we're just going to plug in our initial value. So 0.00623 for that one, 0.00414. And again, in this case, we do actually have an initial concentration over here on our product side. By calculating Q, we determine that we are heading, basically this reaction is not at equilibrium, but to reach equilibrium, it does need to go to the product side. So like we've been doing, it's going to be minuses on our reactant side, and it's going to be plus on our product side. And again, we want to make sure we do get that 2 in there for the coefficient. We're going to then just bring everybody down here, and we'll get 0.00623 minus x, 0.00414 minus x, and 0.0224. And this is again plus 2x. Sometimes people are so used to writing minuses at this point with x's that they kind of go minus here as well. So you want to make sure, again, that it is plus here on the back end. Any questions on sort of the ICE table? Okay. So this again, just like we did in the previous problems, going to go into our expression, which is HI. And again, that's the earlier question when we came back. You do want to make sure you do square it here. And that is going to equal 54.3. We're going to put everybody into their proper places for a bunch of fun math coming up. All right, so we got 0.0224 plus 2x. We are going to square the top guy. We're going to take 0.00623 minus x, 0.00414 minus x, and that is going to equal 54.3. All right, so this is a fun math going on at this point. Or you just go to the next problem, whichever one works better, I suppose, but you probably should give it a go. So we got a lot of, what do they call that? Factoring, foiling, making dinner, whatever that is, making pies. I'm not sure what they call these things anymore in math, but we're going to basically have to sort of factor out everything going on up on top and the bottom, right? So again, kind of multiply both just to remind everybody kind of together. So I'm gonna go to the next page and just kind of work all that out for you so you can hopefully end up with something like what I got here. All right, so in this particular case, if we factored out the top, and again, depending on a little bit of rounding, you should end up with, let's see here, it looks like 0.0005018 plus 0.0896x plus x squared. If you factored out the bottom, we'll go with 2.58 times 10 to the minus 5 minus 0.010, which I can read my writing. I'm gonna go with 37. We'll go with that. And plus x squared is equal to 54.3. So again, that's what you should sort of get there if you factored out the bottom and the top. Again, maybe slightly off with maybe a little different rounding going on in that particular case. Our math journey here continues as we then take everything on the bottom. We're going to multiply it all the way over there to the other side. And that's going to give us up on top still, or on the left-hand side, nothing is changing. And I know I'm going to run out of room, so I'm just going to write it underneath equals. And when we multiply it to the other side, looks like 0.0014009 minus 0.563091 x plus 54.3 x squared. If you're still on this problem at this point, and then if you go to the next one, we're then going to bring everybody to the right-hand side just to keep our x squared positive. You don't necessarily have to do it that way, but I'm just going to bring now everybody on my left-hand side here to my right-hand side. And if you do all that good stuff and combine it, you will end up with 50.3 x squared minus 0.653 x plus 0.000, we'll go 8991. Again, might get a slightly different answer depending if you did a little bit more rounding than I did in terms of that. And that would be our quadratic formula. Any questions on that?
Wouldn't it be 53.3 instead of 50.3?
No, because we have, I'm sorry, I should have, there was, this was 2x up on top. So this should have been, my bad. I'm sorry about that. That was, I might have said it. That's 4x. Sorry about that. So that 4x should be here. Thank you. I think I said it, but forgot to write it there. So let me just kind of clean up here. Yeah. So when you factor this guy, it's actually 4x squared because it's 2x on both sides there. So that should be 4x squared. Thank you. 4x squared. There you go. I think everything else should be okay, I think, at that point. So this would be our A, our B, and our C that would go into our quadratic. Any questions on that? I think everything else looks okay. Thank you. Okay, so now we're almost there. We're going to go into our quadratics. So that's going to give us, and remember, x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So that's going to give us minus, minus, so that's going to turn that into a positive 0.653 plus or minus the square root. If you kind of do everything inside the square root, you end up with something like 0.24551. And then if you take the square root of that, you will end up with 0.495 at that point. And 2 times A, which is 50.3, would be 100.6 on the bottom. Again, this is going to yield us 2 answers. So if we do our x going the plus way, that would be 0.653 plus 0.495 divided by 100.6. That's going to give us an x value of 0.0114. If we do our subtraction, 0.653 minus 0.495 divided by 100.6, that is going to get us 0.00157 as our 2 possible x values. And here, as we were just talking about a minute ago, we get 2 positive values, but it really is going to be the equilibrium line that's going to determine it for us, which one is Not the best one. So before I flip the page, if we just remember our initial concentration of H2 was 0.00623, and it's going to be minus X. So that number is less than this number, which means this guy would give us a negative number if we put it back in. So that would not be the right one to choose in that case. That means that this guy over here should be our winning value, hopefully. And if we do that, we're going to put that back in to the equilibrium line. And I'm going to do that on the next page. Is everybody's okay if I flip it? Yeah. Okay. So going again back to our equilibrium line, our H2 at equilibrium was 0.00623 minus X, which, what did I get there for that X? 0.00157. 0.00157. And that would get us 0.00623 minus 0.00157. It's going to give us something like 0.00466, again, molarity as we need units. Our I2 at equilibrium would be 0.00414 minus X. And we will end up with 0.00257 molar. And lastly, our HI at equilibrium is going to be 0.0224. Remember, this is plus, not minus, 2 times X. So 0.0224 plus 2 times X. Looks like 0.0255 molar. And these should represent our equilibrium concentrations of everybody. Any questions on any of those? And I would recommend, obviously, you can see there is a lot of little steps along the way that can make this go really bad for you. I would probably, just to maybe verify, stick these numbers back into your K value to make sure you didn't screw up anywhere there going through that quadratic, which happens a lot, to me included. 0.0255 squared divided by 0.0466 and 0.00257. Looks like 54.5, which is fairly close to sort of where we started with. So we at least know we probably didn't screw up somewhere. Again, at this point, if you get some back to this part and you check it and you got like a K value of like 300, then definitely something went wrong. And my guess is in the factoring part or something like that. Again, one small little error somewhere can throw sort of everything off. Any questions on any part of that there? Okay, so this is obviously another type of equilibrium problem where you do need to use quadratic formula. It's a little bit more, I would say, not complicated, but a little bit more involved than the first quadratic type formula. And you really do want to be careful along the way here when you're doing things like on this slide, that you don't forget something like I did on the 4. That would not have been great, you know, if I didn't have it written down. But you want to just make sure you're factoring. Your minuses, pluses get a little crazy sometimes along the way as well. Any questions on any of that?
Yeah, I had a question for you. So after you did the quadratic formula, you chose to do H2 to like figure out which one was correct for the answers. Why did you use that one? Did you just use like, could you use any of them, or did you use that one specifically for a reason?
You could. I specifically, the simple answer is it was like the first one, so I just kind of chose that one. But you could look at I2 as well, and you would come to the same sort of conclusion if you looked at it. It started with 0.00414 414. It got really big on my side, so I don't know how it looks on yours. But again, you can see that the starting number there is obviously less than that x value as well, and that would give you a negative. You actually would be okay with the x value for the HI, and perhaps, I don't know, maybe in this one you might not be, but you could actually just look at any one. If there's just even one that it's really not going to work for, it's not going to be the right one. So sometimes it's really easy just to kind of look at the equilibrium line and go, oh, it's definitely bigger than that number, so that's going to give me a -1. So you don't have to really worry about it at that point. But you can literally look at all of them, one of them, and again, you're just looking for at least one that it won't work, and then that's not going to be the right one.
And you want them to be positive by like,
Yeah.
Okay.
So in terms of at equilibrium, just in general, right, we typically don't have any negative concentrations. So they do have to be all positive numbers. We don't really have any negative pressures if we do something with pressures or anything like that. So at equilibrium, you do need to end up with the value for those concentrations or pressures, if they happen to be pressures, to be positive numbers. And if it ends up giving you a negative number, then not so good. Yeah.
Thank you.
You're welcome. Other questions? Okay, so I think we'll stop there. We have one more example we'll do, but we're going through some different types of these problems. And again, you could kind of expect, any of these type of things, type of problems when we do these things. And, you just want to, if you can solve it in an easier way, sometimes you want to take that approach if it's sort of a legitimate way of doing it.